No pressure.
Wow. Hi, my name is Frankie Tang. I'm a third-year computer engineering major at UCSD. I'm working under Optical over there, and Professor Bowers for optical switches with Microring Resonators. So, why should we use optical fibers in the first place? Optical fibers use light to transmit data, and that means there's no electromagnetic interference or noise, because noise is one of the biggest hindrance in data transmission today. They require very little real estate, so they're about the width of your hair, and the devices I'll be designing are even smaller, so that would be good. It's very energy efficient. Data is transmitted through light, so very little heat is dissipated, and heat's one of the biggest factors in power consumption in electrical devices today. And it's very fast. So our coaxial cables today transfer data around 100 megabits per second, and optical fibers can transfer about 15 terabits per second. That's around 150,000 times faster. But the problem is we can't take advantage of that because transceivers today are too expensive and inefficient. And the way we transfer optical data right now is we use optical modulators to turn light on and off to simulate binary data. And the rate at which we can do that is around 40 gigabits per second, heading towards 60. And that's still not fast enough for terabits, or to terabit scale. So the solution to that is to superimpose multiple frequencies of light into one fiber and use optical switches to filter out the data that we want. And that's optical switches like mine will be used for that. So before I get into optical switches, I want to talk about what microring resonator is. Microring resonator operate under three concepts: switches, resonance, and optical coupling. A switch allows the creation and transition or termination of connections. I'll be working this summer on the transition of connections. Resonator reinforces the frequency of a waveform, such as light or sound. And optical coupling happens when you have two waveguides very close to each other, such that when light propagates through one, light will lead to the other waveguide. And all three of these will create an optical ring resonator. As you can see here, light going through here and resonating in this ring and redirecting light through this way. So this is very good because, again, it can redirect light, and we can change the refractive index by applying heat or current. And that means that instead of having multiple rings to have filter out multiple frequencies, we can just apply current to change that. So these are graphs of transmission versus wavelength. This is the transmission of the through port, which is here, over the input. So light will go through here and throughout the through port. As you can see, there are peaks and troughs. The peaks are when all the light is going through this waveguide. The troughs are when very little light is going through the through port and most of the light is going through the ring and redirected towards the drop port. So this is the transmission of the drop over input. So wherever intensity of light is here and intensity of input here. You can see that this is basically a flipped graph of the previous graph, because when less light is going through the through port, more light is going through the drop port because light is redirected this way. So you can see here the graph peaks and troughs align because as less light goes through the through port, more light is going through the drop port. And this ring resonator is actually very inefficient because you want most, if not all, of the light going through here. So many of you may have noticed that I said transmission versus wavelength, but the x-axis is actually denoted by phi. That's because the resonant wavelength is embedded within the variable phi, and you can derive the resonant frequency using these formulas. And this is a superimposed graph of the transmissions. This is a drop, and this is a pass for the through port. So this is an optical crossbar switch, and it's made up of 4 ring resonators. And these three rings resonate at the same frequency because they have the same refractive index. And this will have a different refractive index, so it will not resonate to the same wavelength. So when I put light through here, it'll enter, it'll resonate, and be redirected up. And because this is not resonating at the same frequency, all the light should be going out this port. So the way I'm going to simulate this is to use these two components to simulate real data. This will generate electrical data going out this port and this port. This will go towards the reference, so it will be used as a reference in my eye diagram. And then the other one will go to a light modulator, which will convert electrical data to optical data. And this will be outputted into my circuit. And then whatever input will be coming as optical data to my photodetector to convert from optical to electrical data. And then using my eye diagram, I can compare the input to the reference to see what the bit error rate is. So this is the circuit that I made in accordance to the diagram I showed earlier. And this is both of them put together. So the bit error rate is the amount of error in the bits per amount of data transmitted. So for example, a bit error rate of 10 to the negative 9 is one error per billion bits sent. Generally, the golden standard is to stay under this number. So these are the graphs that I got from my simulations. So the bit error rate of my graphs is around 10 to the 200, and 10 to negative 200 plus scale. So from this data, I can tell that this index is the optimal index for my transmission, because that's when the bit error rate is lowest, which is what we want. And this is transmitted at 1 decibel meters for power. And I found out that if you increase it, the bit error rate actually goes down. So this data shows that as I increase the power, the bit error rate increases. But because there are so many parameters, I want to experiment a bit more before I confirm any of this data. And the reason why I'm doing all this is because I want to help my mentor Aklesh to simulate more optical switches so I can understand them and simulate them at the same time. And in the future, I would like to calculate the crosstalk, which is the amount of power going to the side over the input power. So how much power is leaking to the side over the input power, and it's characterized by this equation, which is also in decibels. I'd like to thank, that's it. And I'd like to thank my mentor Aklesh and Professor Bauer for this opportunity, and Wendy and Jens for helping us with our posters and our PowerPoints, and every one of my fellow research interns and these groups. Thank you.